All right, so welcome everyone. Thank you for joining us. Today we have the pleasure to hear Philipp Hoehn, who will tell us about quantum frame covariance in gauge systems and gravity. Please.
Yeah, thanks very much for having me. So this talk is somewhat loosely based on a couple of these papers that you see down there in the bottom left. So it's not really written like this in any of these works. It's kind of a melange of some of these things in there. And it's also a bit informed by work in progress, and in particular also work that will appear hopefully soon with Sylvain Carosa. So, right, so the talk is about quantum reference frames, or reference frames more generally, in fact. So this is a topic that has received quite a lot of interest in different communities in recent years. And there's gauge theories, there's gravitational physics, there's quantum foundations and quantum information, and a priori, the motivations for studying reference frames or dynamical reference frames in these different fields have been somewhat different. And so what I want to do in this talk here is, when I talk about reference frames, I don't really want to focus so much on the works that have been done in the individual communities or different fields, but I actually want to try to give a sort of more connecting overview over it and discuss actually connections between the different fields as far as reference frames are concerned. And in fact, there are quite a lot of connections, and I will hopefully make some of those a little more precise. Since I'm going to be operating somewhat at the interface of different fields, some of the things I will say are maybe not completely new, but I will try to put them in a different light or make them a little more explicit from maybe a new perspective. And one example is edge modes in gauge theories. I mean, they've been called reference frames before, but here I will try to make it a little more explicit, the connection with work we've done in recent years. So yeah, let's get started. Or maybe one thing at the very beginning is, since I will be talking about dynamical reference frame, maybe let me get out of the way what I actually mean by that. So by reference frame, I will mean some kind of system. So suppose we have some symmetry group given, it could be gauge symmetry group. And a reference frame will be some system that I have in my total system. That is described by a configuration space that's of the dimension of the group. And what I will require is that the group acts faithfully on that reference frame configuration space. Now, ideally, or if we want to have ideal frames, we would want to have even more than that, not only a faithful action, but we would even want to have something like a transitive and free action on the configuration space, so that the configuration space is in fact a homogeneous space, in which case we can actually use the configurations of the reference frame to parameterize the orbits that the group might generate in the state space of whatever theory we're actually looking at. And so we will use, in fact, these, one thing I should say is these configurations of this reference system. This is what we're also going to call the orientation of the frame. Could be the reading of a clock, position of a particle, or something else. And indeed, what we want to use is these orientations is to basically parameterize, to give us a dynamical coordinate system for the G orbits in state space. In the end, these reference frames, they can be particle positions, clocks, edge modes, reference fields, and so on, as we will see. Now, I will start at a very basic level. So I will not start in gauge theories. I think it is useful to take a somewhat more operational point of view that comes more from the quantum foundations community. Then I will try to work myself towards gauge theories and maybe gravity. So let's do some very basic considerations. So suppose we're given some system that may be a bunch of particles as here. And the premise is that the system is subject to some symmetry group G in such a way that different states that are related by group action, that they are indistinguishable when the system is considered in isolation. So for example, we could have something like a rotation group acting on this. So and the premise is that we can't distinguish this internally. But what we can of course still do is we can pick some subsystem of the system of interest and try to use that as an internal reference frame. So such as that particle are there, and then we can try to describe the system from the inside, basically, relative to one of its subsystems. Now, I can, again, do a transformation that's physically, again, indistinguishable. And so basically these states that are related by a group action, they will form members of one and the same relational equivalence class of states. And in fact, in the end, we can consider them, so they contain the same information, it's the same physical situation, at least as seen from the internal perspective, but it will give rise to different descriptions of the same relational state. And we can also view that as, for instance, different internal frame perspectives. So we could choose a different particle to define internal description. And basically, these relational equivalence classes of states, they contain, therefore, the information about all the internal perspectives. And they're, in that sense, perspective neutral. That's what we'll see later on as well. Now, so far, we've considered the system in isolation, but now what happens when we want to go beyond it? Maybe there's a little more in the world. So we could have, for instance, now a laboratory that defines some kind of external frame. And what I've looked at before, these transformations, they're indistinguishable. The physical situations are indistinguishable relative to the internal frame. But now when we embed it in a larger context, we have to be a little careful because we have to distinguish the situation that the system moves relative to the external frame, in which case that's a distinguishable situation relative to that laboratory. But there could, for instance, also be the situation that the whole thing is moving, in which case it's also indistinguishable relative to the external frame. And from the point of view of the internal physics of the system, well, there's no way to distinguish these things. And that's, of course, fine. But when we want to actually describe the subsystem physics internally, we don't have to care about these things. But if we want to know a little more about the world, how that subsystem might couple to its environment, then these things actually become relevant. And here we have to worry about this thing that we're basically extending the Heisenberg cut. So we're basically turning external reference frames internal. So this Alice there, who was external before, has now become internal relative to maybe other frames. So this sounds very simple, but it's something that we need to worry about. And there's also something when we see edge modes that we have to take care of. So there's a couple of possible interpretations here. So when it comes to the external frame and the different fields and quantum information foundations, it could just be a lab frame. In gauge theories, there will be edge modes. You can interpret those as edge modes. In gravity, there can also be edge modes, but there can also be some reference fields that I might want to use to develop relational observables for other degrees of freedom that I might be interested in. But it could also be some asymptotic boundary that the space-time might feature on which diffeomorphisms no longer act as gauge symmetries. And as far as just looking at the internal physics of the system of interest is concerned, and maybe we're not considering the external frame, we're only looking at internal perspectives. There might be two interpretations of it. A more operational one is that, well, maybe there exists an external reference frame, but we don't have any access to it. So you can, for instance, imagine the situation that you have Alice and Bob that are observing some subsystem, and they have external frames, but they don't share a reference frame, but they may want to nevertheless agree on the description of that subsystem. And in this case, you will have, so then they can choose some subsystem, some quantum subsystem, and basically, well, the situation you get is that you have classical external observers who choose maybe internal quantum systems as reference frames. And of course, you can have the same situations in finite region gauge theories. Maybe you're only interested in the physics within a finite region, and that's how it couples to the outside. But there could also be a more fundamental situation where you're reaching the end of the world and there isn't anything left that could be external, so that no more external reference frames exist, such as in like closed universe, quantum gravity, or quantum cosmology, or even in Wigner-Friend scenarios in quantum foundations. So in that case, you rather get something like quantum observers who can be in relative superposition. So the interpretation is quite different, but in fact, formalism will be the same. Okay, so now let's maybe look at a very simple illustration of these things in one of the simplest possible examples, namely a bunch of particles in one-dimensional space subject to translation invariance. So it might be a little silly to look at these simple things, but they make some of the statements rather transparent that one can also use in gauge theories later. So suppose we're given some subsystem S of 3 particles, well, subject to translation invariance. Well, I can translate my system that's subject to gauge symmetry, at least from the internal perspective. I have a translation generator, and of course that leaves all the the relational data invariant. But now I can basically, instead of choosing some internal perspective within the system, I can extend the Heisenberg cut and add a reference system on, and let's call it R. This is now still, it's an external reference frame to S, but it's internal to the total system, and you can call that also an edge mode already suggestively. And now we can use this additional degree of freedom, in fact, to turn all the degrees of freedom of S into gauge invariant ones, because now we can, of course, look at all the, for instance, all the relative distances of ABC relative to R. We can write them as relational observables. And you can write them down in this power series representation. So that's, you know, Bianca Dittrich's power series representation for relational observables. And well, that corresponds to the basically to the question, what's the position of particle I when the reference frame is in position X? And so here X, we can interpret this as the frame orientation. It's the, for a position reference frame. So it's a reference frame for the translation group. Yeah, the orientation is the position. Yeah, so one thing to note, of course, and it's very simple here, but it's still important that, you know, we get an increase of the number of gauge invariant degrees of freedom compared to the previous situation, because we can now distinguish the relation of S with the additional reference frame that we have. And it's not that, you know, we have all of a sudden that we can distinguish, you know, gauges from the previous situation, because here, of course, afterwards, you know, the absolute position of the system still remains inaccessible. Yeah. So, but now what I mentioned before, the translation of that system S, when we embed it in this larger system, we have to be a little careful, because in the larger perspective, it could be 2 things: that we translate the whole thing, in which case nothing changes. The relation between R and the system is unaffected, and this is then a gauge transformation in the larger system. Now, but of course, we could also have the situation that the translation is actually a relative translation between S and the reference, in which case the relation between R and S is changed. It's internally indistinguishable for S, but yeah, the relation with R is changed. And this is what we can call symmetry. And in fact, that's when I talk about gauge transformations and symmetries here, this is also what we will see later in the edge mode business. So yeah, now here we can distinguish these gauge transformations. I mean, just suggestively, I mean, if you like the covariant phase space, you can, of course, look at the constraints that you generate through a vector field that's in phase space that implements these gauge transformations, and not surprisingly, you just get the total momentum to be 0. And likewise, you can look at the symmetry transformations, and in that case, they give you a charge, where here you only translate the system relative to the reference. And the charge that you get is just the total momentum of the system. And on the constraint surface, that's of course just minus the momentum of the reference frame or of the edge mode. Now the important thing here is that what we see is when we look at this charge, what it actually generates. I mean, that's the symmetries. And what we can see here is that the symmetries, in fact, generate frame reorientations. So if you look at this equation here, the action of this charge on such a relational observable, what it does is it basically generates translations in this parameter X here in the relational observable. So that's a message to take away. Symmetries are actually frame reorientations. And now let's consider the situation that we have an additional reference. So we're extending the Heisenberg cut further. So we basically have now 2 edge modes. And now when we have 2 reference frames, we can ask about reference frame changes. And we have to compare that to frame reorientations. So first of all, let's consider again edge mode 1. Well, we have now all the relative data of S relative to R1 and also of the second mode, edge mode relative to R1 in terms of these relational observables. Now remember, the symmetries are frame reorientations. I can look at these translations here and well, it's equivalent to translating R1, but not the rest. And that's equivalent to translating this parameter in the relational observable here, these guys, that's of course equivalent. And one thing to note is, I mean, there exists of course a special reorientation of the frame R1, which is a relation conditional symmetry. And that's, I can of course translate R1 simply by the relative distance with R2, so here. So that lambda, that by how far I translate is given by the relation observable, the relative distance. And so basically I collapse these things. And then, you know, when I look at the change of the relational observable under this transformation with lambda given by this here, well, what I see is all of a sudden these relational observables that were before Qi minus QR1 plus X1, they now become the relative distance with R2. So it appears as though this symmetry transformation is also something like a reference frame change, because it appears as though I'm now describing everything from the perspective of reference frame 2. But of course, we have to be a little careful with this because it's not actually reference frame change, because we have changed the physical situation. After all, we have moved R1 relative to the remaining degrees of freedom, and we've collapsed it with R2. And so the relative distances have actually changed. And so, and of course, reference frame changes, they should not actually change the physics. They should rather change the description of it. And so symmetries are frame reorientations, but they're not reference frame changes. Just to highlight that. Now, what are then reference frame changes? And in fact, they're nothing but coordinate changes on the phase space, on the reduced phase space. So on the gauge-invariant phase space, where I take the constrained surface and I mod out, so I just go to the space of orbits. And here in this case, well, what happens? I mean, I can, of course, I mean, you know, I change the parameterization of my gauge-invariant data. I just measure all the relative distances relative to R2 now. And of course, I can do that equivalently. There's no problem. And ultimately, in this simple case, you know, all these relational observables here, in fact, they're canonical. They form canonical pairs. And a reference frame change, what does it do? Well, it takes these relational observables of the positions of I relative to R1 and their momenta, and the second reference frame relative to the first, and I map that to the canonical pairs of the particles in S relative to the second reference frame now, and the first reference frame relative to the second reference frame. And now at positions of X2 of the second reference frames of the edge mode, if you want. And so these are not arbitrary coordinate changes on that phase space, but they're changes of relational observable families that are associated with frames. And now, this already gives something, like it gives us a notion of a relativity of subsystems. Because, well, we have now these two descriptions, so relative to R1, and we also have it relative to R2. And so this gives us this canonical transformation that I just showed before. And actually what that induces is a refactorization of the observable Poisson algebra on that, so of the Dirac observable Poisson algebra on that reduced phase space. So the total algebra of invariant observables, I can write it in these simple cases as the relational observables of the system S relative to reference frame 1 times the relative relational observables of reference frame 2 relative to R1. And well, I can just write it also then in reverse order where I change the reference frames. And this is a refactorization of the observable algebra, because it turns out that you can easily see that in fact, what the system is relative to R1, the observable algebra is not the same thing as the system relative to R2. And that, yeah. So in that sense, in fact, the notion of subsystems becomes actually frame dependent here. So the reference frame 1 and reference frame 2, they mean two different things when they talk about the system, or different degrees of freedom, rather. Okay, so let me maybe say something. So I didn't really talk much about this perspective neutral approach. Maybe let me say in one slide how this relates to this perspective neutral approach to frame covariance that we developed in recent years. So basically, what this gives you is a gauge-invariant framework for reference frame dependent physics. So here, just giving you the classical picture, I will say a little more about this in the field theory context later, and then we talk about it in the quantum theory. So we have the constraint surface, C, and also the space of orbits. And we can, in fact, interpret these as perspective neutral structures, both of which they contain basically all reference frame perspectives, right? Because, I mean, for example, the observable algebra on it is A-phys. I mean, it's neutral a priori with respect to which reference frame I want to describe it. I can factorize it in different ways, but of course, it encodes all of these different choices. So in that sense, it's reference frame neutral, and we just call it perspective neutral. And now we can go a step further and actually remove some of the redundancy in the description, which is, at least when you're on the constraint surface, of course, you have a redundancy coming from the kinematical data and the constraints. And basically going to frame perspective is now removing that redundancy. And you can basically do that through gauge fixing. So you can associate, for instance, the simple case, you can just gauge fix the position of the reference frame to be the origin or something like this. You just declare it to be the origin, and then you gauge fix your gauge invariant description. And well, if you look at this diagram here, I mean, if you take the space of orbits, what I mean by gauge fixing is basically I associate with the orbit the point on the orbit in the constraint surface that cuts the gauge fixing surface. Then I can just remove the redundant degrees of freedom, and then I get a gauge fixed reduced phase space, and I can do that in a different perspective as well. Then I have these two different internal perspectives without any redundancy. And in fact, I can map from one description to the other by inverting these maps, and I can concatenate them, and it takes the form of coordinate transformations. So I will say a little more about that in the field theory case later, but that's kind of like a crash course here in on this perspective neutral approach. Okay.
Sorry,
yeah.
Can I ask a question, Philip?
Yeah, sure.
Sorry, I got lost. Now, these phase spaces are the same. I mean, are equivalent. You have this map, the bottom phase spaces, but how does it relate with the previously? You said that these two different algebras were different in the previous slide.
This year, you mean? Or?
Yes, yes. I mean, maybe it's not related, but
no, it is related. So, okay, that is a good question. So, I mean, the thing is that this algebra here, I mean, that's basically the algebra of Dirac observables on C, and well, it's the algebra on the space of orbits. And the point is, I can write it in different ways. I can I can interpret it in terms of relational observables relative to the reference frame 1 or reference frame 2. And depending on how I do it, this gives me you know, a different factorization of the total algebra. Now, here in these reductions, I mean, you know, each of these factors contains a generating set of algebra elements. And those are kind of the natural observables that you should choose when you go into the internal perspectives, basically, that you can nicely gauge fix, for instance. And so, and basically when you gauge fix those, I mean, I didn't really talk about it, but for instance, let's say let's look at this observable here. So this is relative to R2. I can gauge fix it by just declaring QR2, the position of R2 to be the origin, so 0. Then this whole thing is just, you know, QR1 plus X2. So it's just a degree of freedom for, you know, the surviving reference frame. And I can do the same thing with the other degrees of freedom here. So after the gauge fixing, I'm only left with the kinematical degrees of freedom of the system. And so this I can do. I mean, when I go into these internal perspectives, I get a particularly nice form when I use the relational observables that are associated with the frame perspective in which I'm going. The thing is, I can of course also gauge fix the relational observables in the other factorization in the same way. So such as these ones here, I could still gauge fix them. It's just also by declaring QR2 to be the origin, this will only do something to this one here, but it won't do anything to these here because QR2 doesn't appear in here. And so rather, in that case, these relational observables, they will be rather composite degrees of freedom of the surviving degrees of freedom A, B, C, and R2 that I want to describe in the in a corresponding frame perspective. So in that sense, basically, when I look at this refactorization here, so what will happen is when I look at the frame perspective R1 and I look at these observables here, when I reduce it, it will really they will really look like sort of local observables relative to the what is the system or R2. But if I look at, for instance, these relational observables relative to R1, then they will look like composite objects. So you can do it, but it's just telling you basically that this gives you sort of a refactorization of what you mean by subsystems in your phase space. So you can see that refactorization also in these reduced phase spaces. So, and you have to be careful with it when you translate from one to the other. But so I glossed over this here because I didn't want to go into too many details. But that's
okay. Thank you.
Okay. So, okay. Whoop. Okay. Yeah. So maybe let's move on now to gauge theories, and let's talk about edge modes as reference frames. That's of course something that many people have already talked about. So here, let me try to give you, a perspective on it that connects with what I just said before. So we can look at some finite region, and it's a spatial subregion. That's now our subsystem S. And suppose we were given some compact gauge group G, and we have some connection A. Then we can, of course, look at the local gauge-invariant physics in that region, some holonomies, Wilson loops, and maybe the field strengths. And here again, of course, the physics is entirely indistinguishable under these gauge transformations, where the star means group action. Sorry, stupid notation. But now we can also, as before, extend the Heisenberg cuts if you want. We can use this M prime, go to some larger region, we can use M prime as an external observer of M. And there exist many different ways in which one can do it. So here, one way of doing it is we can, for instance, I'm just going to do it locally, we can consider some charge psi on the boundary of M prime, for instance, and we can send in a Wilson line and shoot it to the boundary of the region we're interested in, to some point X. And then we get such a group valued reference frame. So this here is the Wilson line. So so this U of X is of course it's a group valued frame. That's what we can call an edge mode at X. And the important thing is that this U is dynamically independent of the other degrees of freedom that come from the region M alone on the boundary. And that's basically, if I shoot it in orthogonally, I mean, it will depend dynamically, of course, on what happens in here. This is something you can't predict by only being an M. And in particular, it will also involve, for instance, the normal component of A here on the boundary, which isn't part of the canonical data on the boundary. And now, well, if you look at this object here, if I throw a gauge transformation of the larger region on this whole thing, then what I find is that the gauge transformation acts by left multiplication on that reference frame. So in conclusion, what we have is that we have now this U is now, it extends the phase space for the boundary of that subregion we're interested in. And it's a faithful reference frame for the gauge group G because it transforms nicely. So we can view that as now an external reference frame that's describing how M couples to its environment, but an external frame that has become internalized. And now that we have this frame, we can also build relational observables or dressed observables similar to how we did it in the particle model before. And so suppose phi is now some function of A or the field strength on the boundary. Then we can define a relational observable in this form here, where we have, and this will correspond to the question, what's the value of this functional phi when the reference frame U is in its orientation G prime. So G prime here is a fixed group element. So it's like a parameter, really. You can define it, this object in this way here through the group action. So you basically use the group valuedness of the frame to define this relational observable here, and you can convince yourself that that this object is gauge invariant. And when you write it out, well, it looks like this here. And one example that we have is, for instance, we can turn the connection A into a gauge invariant connection. We can call it radiative if it lives only on the boundary, really. And we can give this parameter G prime, and if you write it out, it will have this form here. So it's like a dressed observable. It's dressed by the reference frame. And in this way, we can really turn all the boundary degrees of freedom of M into gauge invariant observables through the relation with the edge mode, or rather we should have an edge mode field, of course, on the entire boundary. And so in this sense, we are of course increasing the number of gauge invariant degrees of freedom on the boundary. And that's because we have now additional dynamical degrees of freedom. It's not that all of a sudden we have maybe more photon degrees of freedom. It's just that we have now an additional frame degree of freedom, and the additional gauge invariant information or gauge invariant degrees of freedom that we get is simply describing the relation of the subregion with its environment. Now here we can also distinguish again gauge transformations and symmetries. That's of course something that people have already done, in starting with Laurent and Will Donnelly. And we see that here again. So gauge transformations, they act by left multiplication on the frame, as I already indicated up here. And now symmetries are again frame reorientations. And they act in fact by right multiplication of the frame. So, so what you can see here is if I take a right multiplication of the frame and the relation observable, that's equal to changing the orientation of the frame here. Okay, so in that sense, we give maybe a nice interpretation of these symmetries versus gauge transformations. And then, as many of you will know, of course, those gauge transformations, at least for the subregion, they will lead to constraints, the precise form of which you can find in these references. And if you look at symmetries, they will lead to non-vanishing charges. And these charges are then now with what we have said here, these charges are then really the generators of these frame reorientations, so of the edge mode reorientation, if you want. And now, as in the particle model, we can extend the Heisenberg cut further and further. So we can go to a larger region, can have maybe an additional charge on that boundary, and we can even go much further than that. And we can have maybe further charges and shoot in holonomies. And then we will get more and more edge modes or reference fields at this point here that are dynamically independent because well, they carry information about different regions of or different regions really. And so basically, what happens here is that we are extending the phase space on the boundary. With every extension of the Heisenberg cut, really. So we get new edge modes, new reference frames. And yeah, and in this sense, you can view the extending of the Heisenberg cut as a refinement operation in some sense, because we're getting more and more degrees of freedom on the boundary that give us more and more information about how that subregion M actually couples to its environment. So yeah, and now that we have talked about these things, we can, when we interpret these reference frames as the edge modes as reference frames, we can also think about reference frame changes. In the future, of course, these things become a little more complicated, but basically the story is qualitatively the same as before. The the reference frame changes are not symmetry transformations, but rather they're again coordinate transformations. And here in the field theory case, there are simply really field redefinitions. So there are coordinate changes on the extended phase space for whatever problem I'm looking at, where I'm looking at the extended phase space still for the subregion and the constraints that come from whatever larger problem that I'm looking at, but you know, associated with the subregion. And then I can again look at these relational observables that I talked about before. I mean, there will be many more now, and of course I have to do that across the boundary. But basically, I can look at the relational observables of the fields that come from M itself. Let's call them phi I relative to some reference frame U1, and I can also look at the relation between the new reference frames and the old reference frame, and then I can map that somehow to basically the analogous observables, but now relative to different choice of edge mode. And these transformations, they should in fact be homomorphisms, because these relational observables, they define you algebra homomorphisms. And again, it's not an arbitrary coordinate change, but it's or field redefinition on my phase space, but it's again, you know, changing relational observables that are associated with certain frames. Okay, now let me say a little more about the perspective neutral approach in field theory, or the perspective neutral approach to frame covariance in field theory. And maybe here as a, so basically a starting point is we should do something like the covariate phase space. And let's maybe recall how we get a constraint surface. That's something that you can do a la Lee and Wald. Maybe you supplement it by works in recent years by various authors in dealing with boundaries. So whatever problem you're looking at. So we have some field space for, you know, whatever problem it is. Then we have the space of solutions associated with that problem. And then we can look at these projections to a phase space. It gives us a kinematical phase space. The projection is basically removing non-degenerate directions of this presymplectic form that I can define on F. And I can also restrict it to the space of solutions. And when I do that, I will get a constraint surface. And this constraint surface here, well, it will also contain, of course, the reference frame, degrees of freedom, or the edge modes. And now I can go again to something like the reduced phase space, where I look at the space of orbits. And again, like in a mechanical example, I can consider this constraint surface and the space of orbits as a perspective neutral, a frame choice neutral structure that encodes all the frame perspectives at once, similarly to before. And likewise, I can also consider this here, I mean, it's proper phase space, can consider this basically as a perspective neutral phase space, because I mean, I haven't really made a choice of frame yet, which reference frame I want to choose. And at this level, as I mentioned before, reference frame changes are really field redefinitions. And as in the mechanical case, we will get a frame dependence of subsystems, because we're now probing the region M that we might be interested in different ways, in different relational ways. So through different relational observables. And now the thing that you can look at is now also these frame transformations at the redundancy-free level, because here, you know, what I said before, at the perspective neutral level, in principle, you have some redundancy, at least at the level of the constraint surface. And you can also now look at a diagram such as this here, where I can define something like coordinate maps into frame perspective, if you want. So, and this is basically, again, a reduction by gauge fixing. So what I can do is, again, I can associate with, so I can, let's look at this side here, maybe. So this phi 2 is the map that's given by these two red arrows. So I'm associating with you know, some point in the space of orbits. The point on the corresponding orbit in the constraint surface that's intersecting a certain gauge fixing hypersurface. So because I may want to gauge fix, for instance, my reference frame again, I may gauge fix the edge mode, I'm free to do it. And then, well, I can have something that's like a projection that's just removing the redundant degrees of freedom. You don't really need that additional step, but well, you can do it, of course. And then you get a gauge fixed reduced phase space that's describing what's happening in the region relative to the reference frame R2. So I should say this G2 is the gauge fixing of the reference frame 2. And then I can consider this as the perspective or the frame description or the coordinate description, if you want, of reference frame 2 of the remaining physics. And I can do the same thing with my reference frame 1. And I can invert these coordinate maps, at least wherever they are defined. In general, they're not going to be defined globally, just like in manifolds. And that's here in the case, especially here when we're dealing with Young-Mills theories and so on, it's literally due to the Gribov problem. So that's because these coordinate maps are associated with gauge fixing, and gauge fixing are not in general globally valid. So, and then I can, go from the perspective of one reference frame to another by basically concatenating these coordinate maps in this form here. And I always map through the perspective neutral structure, which is like takes over the role of the manifold if you want. And these are like the coordinate descriptions. So in this sense, I can look at the frame field changes as coordinate transformations if you want. Okay, so I mean, this is something you don't necessarily have to do. I'm just giving you this information here because I mean, this is really how we've done this perspective neutral approach in recent years. But of course, the same information is already contained at this level here, right? So I mean, when I'm looking at the field redefinitions here at this level, I mean, that already contains all the information. So here, going to these perspective descriptions, that's just removing redundancy in the description, but I'm not gaining any new information by it. Okay, so let's so much about edge modes in field theory. Let's move on. We came from sort of a foundations perspective and moved to gauge theories. Let's go in the reverse direction. And there's something that's known as the paradox of the third particle in the foundations community. And let's see what we can say about it. So one thing I should say is what I just told you about these corner reference frame changes. Well, so far I talked about classical reference frame changes. We can also do it in the quantum theory. It works analogously. You get this perspective neutral structure. So far we've done it for mechanical or cosmological systems in various works. And here again, the perspective neutral structure is really basically the quantum constraint surface, if you want. And then you can do a quantum symmetry reduction that I'm not going to explain in detail here. It's just can accept that it exists. It's basically just the conditioning on a frame orientation. That's the essential step in it. And that gives me something like reduced descriptions, like quantum symmetry reduced Hilbert spaces if you want. They're not in general equal to reduced Hilbert spaces coming from reduced phase space quantization. They're in general something different. But the quantum reference frame changes, they work in a similar way to how it was done in the classical case. So, so by quantum coordinate changes if you want. Now, I'm not going to explain that much further. Let's just accept that this exists. I've spoken about these things before. And now let's go to what the paradox of the third particle is. So, so this is very much related to what we were talking about before. So suppose we're given two particles, A and B, and now this is, they're prepared in some kind of state like this relative to some external observer. Now what you can do is you can align the state to the perspective of particle A chosen as an internal reference frame. So these authors here, they have not done it in the way in which I'm going to do it now. They haven't used these gauge descriptions or in terms of constraints and group averaging, but it's equivalent what I'm going to do to what they did, and it's more transparent to see what's going on. And so the way you can align such a state to frame perspective, basically what you do is you take your state, psi, you, in some sense, perspective neutralize it by group averaging it. So this here is the projector on the corresponding to the constraint of the symmetry. Sorry, here we're again dealing with translation symmetry. And let's say for simplicity, we're even going to take a billion finite groups. So everything is discrete. But we can choose here literally a coherent group averaging, but associated with two particles now. And so what we're going to do is we're group averaging that state. So we're erasing any information about the external frame because we want to take an internal perspective. And then we just condition it on the frame orientation of A, and that gives us something like this here. And this is what we can call the alignment of the state relative to particle A. And what you find is here, this phase theta that was up here before, it survives in that description. And then you also say, oh, you know, particle A has access, could in principle measure the phase theta. So given our other interpretation that we discussed before, we can also view it as some external observer who does not have access to this external reference frame, but only has an internal reference frame. They could somehow still do measurements that detect this phase theta. And now these guys consider the addition of a third particle, C. And the way they define this addition is that they added relative again to the external reference frame, and it is added in this product form here. And now we can, of course, again internalize it or perspective neutralize it and go to the align it to particle A. And if you do it in this case, you get this form here. Okay, so theta seems to be still around as here, but now what these guys observe is that, well, if you actually trace over the third particle over C, you get different answers when you do it with this state here than when you do it with this state here. In particular, in the first case, I mean, it's obvious when I trace over C, I mean, it's a product state. I mean, I'm just removing this. Clearly, theta is going to survive. But then what you can convince yourself of is that when you trace over this one here, over C, it turns out you will get an independence of theta. And so now, so the reason how they motivate the trace over the third particle is that they say, oh, you know, I can just consider particle C to be really far away, so it's not influencing what A and B do, and so I should be free to trace over it without any physical effect. And so, but then they see, oh, but you know, if I do it in different ways, actually, this phase theta may no longer be accessible. But if you think a little bit about it, I mean, of course, it's not a surprise that there's a difference between these states when you trace about them over them, because you know, psi and psi prime are externally distinguishable. So they're not, and when you trace over C, what you're basically doing is you're doing a trace that that takes an external reference frame into account. That you know, that's not taking into account that when you want to go to an internal frame perspective, that you should be worried about things that are internally distinguishable. And so anyway, so this here they declared as a paradox because depending on whether I add the particle C or not, you know, particle A will have or will not have access to the phase theta on the second particle. And well, they declared a paradox because you know, they claim that if particle C is very far away, that it shouldn't matter. So there shouldn't be any physical difference. But of course, one has to be a little more careful about this thing. So what they really observe is that the alignment and the partial trace don't commute. So they take this initial extended state of ABC. Then when you trace over it, you just get the original states that you had before you added particle C. And you could, of course, and then you can align it, and then you just get what you originally had, something that depends on theta. But now the point is, when you do this alignment, you do a group averaging, and the group averaging you do is now over this two particle group. And remember from before, this is actually a charge of the three particle problem. It's not a gauge symmetry. But conversely, if they first align relative to A, what they have to do is you have to use a group averaging now for the three particles. And this one knows about the relation between AB on the one hand and C, whereas this one here doesn't know about it. But at the same time, you know, this state here and this state, they're symmetry related, so they're internally indistinguishable. So this problem here that they're phrasing is really, I mean, it is an embedding problem. It's associated with the extension of the Heisenberg cut that we were talking about before already. And so we need to be very careful about what we actually mean by tracing, because when we want to talk about what an internal you know, observer or an internal perspective has access to, we have to take into account what is internally distinguishable or indistinguishable. And this is, you can really view this, I mean, as a toy model for boundaries and gauge theories. I mean, the question, of course, is, you know, if I have two regions and some, you know, gauge-invariant degrees of freedom inside each of them, you know, how do I embed, let's say, you know, the information, the gauge-invariant information in this subregion into a larger region? And that's not obviously a non-trivial problem, because you have all the cross-boundary data that's not contained in this region alone. And here in this in the particle model, you know, you can do it for 3 particles as we saw, but you can also do it for many more particles. Obviously, you know, we basically have 2 groups of particles, and the problem we're looking at is how do I embed in a relational way a group of particles into a larger group of particles, and in such a way that when I trace, when I reduce, that I get a consistent reduction that takes into account what are internally distinguishable degrees of freedom. And so, yeah, so basically the problem is how do I embed 2 particles and 2 3 particles relationally? And the statement is really the standard trace is partial trace is wrong reduction rule. It ignores the internal indistinguishability of these states. And well, basically what I said is, can we find a relational reduction rule that preserves this theta? And essentially, this whole thing is related. I mean, it's dual. So when I want to talk about now a reduction, a consistent reduction from a larger region to a smaller region, that's the dual, algebraic dual of embedding the observables of a smaller region into a larger region. Because you can also think of always of a partial trace as being the Hilbert-Schmidt dual of an observable embedding operation from a sort of smaller region algebra into a larger region algebra. And so this is what we want to look at here. But of course, we want to do that with respect to invariant information. So time is progressing relatively quickly. Let me, therefore, there's a couple of other things I want to say. Let me just summarize kind of briefly what happens here. So, why is that not moving? Okay. So, oops. Yeah, so it turns out when you think about gauge-invariant states, there exist 2 different kinds of gauge-invariant states. One you can call invariant states. It's states that have this property. When you conjugate them with a symmetry operation, they're left invariant. And then there's, of course, also the relational states, or what we call physical states, those that are annihilated by constraints, that are just a subset of the invariant states. So these are coherently group averaged states. These ones here are the incoherently group average states. And it turns out that if you want to look at these embedding operations, or then also these invariant notions, gauge-invariant notions of reducing, at the level of these invariant states, it turns out that it will always depend on the relation between the 2 particles I had before and on how I define the relation between the 2 particles I started with and the 3rd particle I added. Because for instance here, if I look at these 2 situations, the question is whether in different branches of a superposition, whether I can consider those as being basically the same relation of that first particle group to the second one or not. And for instance, if I define the relation between the additional degree of freedom and the first particle group in terms of the distance between the first and the 3rd particle, then these 2 are going to be the same relation. But if I define it relative to the relation of between the 2 groups as the relative distance between the 2nd and the 3rd, then these 2 branches are not going to be in the same relation. And this is something that essentially screws up this embedding for these invariant states. And basically the statement is, you can find gauge-invariant ways of reducing here and gauge-invariant ways of embedding, but they will always depend on how you define your relation between the particle groups. And in some sense, so you get an ambiguity, and in some sense, the paradox, you can say, persists here. But now, when you actually restrict further to the physical states, it turns out there exists a natural embedding of the basically of the relational observables for n particles into the algebra of relational observables for n plus m particles. And basically that embedding operation is just coherently averaging over all possible relations between these particle groups. And it's something, this operation is something that in fact doesn't define an embedding for these incoherently group averaged states, these invariant states, but it does define an embedding for physical states, really. And Dirac observables defined on it. So just if you want to know how that looks like, basically you can call that then a relational trace that is the dual to that embedding operation, and it takes the following form. You basically have the group averaging over the three particles you trace over C, and then you group average again over two particles. That's just how it turns out. And when you look at now these states that we started out with in the very beginning that gave different standard partial traces, when you do the relational trace over those, it turns out that they will agree for the two states, and they will unambiguously preserve that relative phase theta, and you will always just get back the original perspective neutral state. So in that sense, one can say that the perspective neutral approach, which works on the physical Hilbert space level or at the level of these Dirac observables, doesn't actually feature the paradox of the third particle. Okay, so let me maybe say a few more words about reference frames and what they can tell us about the interpretation of invariant observables. So maybe let me ask, how much time do I still have?
5-10 minutes.
Okay, yeah, I think that should be enough.
Fine, no worries.
Okay, so whoops, the light just went off here. Yeah, so my apologies for the slight change of style here. I'm moving house tomorrow, and so I didn't manage to do these slides in the same style as before, so I'm recycling something here, but the content still fits. So the problem we're going to look at now is, how do we interpret actually gauge-invariant observables? So that holds for gauge theories, but in particular also for gravity. So basically, now suppose we're given the algebra of gauge-invariant observables for some gravity theory, maybe classical, maybe quantum. So I mean, that's a question that often arises. I mean, how do I interpret such observables? And basically what I want to argue is that reference frames, they provide as a context for interpreting these objects. And reference frames are what we usually invoke in order to give meaning to gauge-invariant or to relational or to diffeomorphism invariant observables, be it in terms of relational observables or dressed observables. And so how can we do this here in this case? Well, or in general, I mean, of course, as you all know, I mean, we can have some kinematical observable algebra. I mean, I'm drawing them as some weird sets, but of course, there are actually some vector spaces, so it's a bit of a bad drawing, but never mind. So we have some kinematical degrees of freedom, maybe some matter fields, some geometric data, and now we can look, for instance, at building relational observables out of those. We can pick some, let's say we pick some choice of reference fields. Let's call them T1A. So A for running over the number of reference fields that we need for the problem. So if we're in 4-dimensional GR, let's say, then we need 4 reference fields. And basically, you know, relational and dressed observables, what they do is they stratify your invariant algebra. So they define orbits inside it. And that's what we should be looking at. So for example, if we want to look at, say, a scalar field, and we want to know what's the scalar field, so it's a relational observable again, when the reference field is in configuration tau 1a, so these are some values, so the orientations, if you want, of those reference fields. then, well, I mean, that will, I mean, you can just write it down somehow in whatever theory you have. That, of course, will define as somehow a 4-parameter family of observables in our invariant observable algebra, so some orbit like this. Now, I can, of course, also look at other relational observables relative to the same choice of reference fields. Maybe I want to know what the Ricci scalar is, or symmetric degrees of freedom, and each of those will define me another orbit that goes through my observable algebra. And I can define a different set of relational observables, maybe relative to some different prescription or different set of reference fields. And that will give me a different set of, in general, of different orbits in my invariant algebra. Now, I can also look at drastic observables, for instance, and there will exist also different ways of dressing observables. We can always think about any of these drastic observables also as giving us a reference frame prescription. So suppose we have some, maybe perhaps a boundary or something, we can attach some platform on it, maybe shoot a geodesic inside, and after a certain distance, we evaluate, let's say, the scalar field, for example. So that's an invariantly defined observable, and it again is a 4-parameter family. So which I denote by this X here. I mean, that's basically the position of the platform on the boundary plus the distance along the geodesic that I'm shooting inside. And so this will give me again some other orbit in that invariant algebra. And if I do the same dressing prescription to other kinematical degrees of freedom, well, I will again get some different orbits. And of course, I can find some different dressing prescription. Maybe I want to use light rays to shoot inside instead of space-like geodesics, and then evaluate the the field there, and that will give me again, if I do that, a bunch of different orbits. And now, if I have, let's say, some observable that sits at the intersection of these different observables, then it will reside in different orbits, and that means, in fact, such an observable will admit one and the same abstract observable in that algebra will admit multiple interpretations. And so the point is, in fact, this is something that you should in general expect. So in simple systems, you can explicitly see that this happens. So for example, especially if you have a global ideal reference frame, so that covers whatever region I'm interested in, such that I can write every element of my invariant algebra as some maybe relational or dressed observable relative to this choice of frame or this prescription. So in mechanical systems, you can see it in some examples explicitly that you can do it. And if you have several global ideal frames, then of course you get different ways in which you can sort of stratify one and the same algebra. So you are guaranteed that you get that different algebra elements will actually lie on different such orbits. But this will also be true in field theory if I have something like global ideal frames that they will actually maybe cover the entire algebra in terms of the orbits. And even if I don't have ideal frames, the argument will generally still hold locally in that algebra. So the statement is then that one and the same diffeomorphism invariant observable, so abstract observable, can be a relational or a dressed observable in many different ways. And so this means that one and the same abstract invariant observable actually admits multiple physical interpretations in terms of different choices of reference frame. And so this is what I mean when I say that reference frames actually provide the context in which you can interpret these gauge-invariant observables. So it's a bit analogous to what happens in quantum mechanics, where you can have, of course, a bunch of observables on your Hilbert space, and but then usually in order to give a complete description or interpretation of it, you have to give some kind of measurement context in which you're measuring that observable. So this is a bit analogous here, that you can think of these reference frames in some sense as providing the context in which you are allowed to interpret a given abstract invariant observable. But the observables will in general be part of different contexts. So I think there's something that maybe is a little underappreciated, but I think it's conceptually an important point as regards the interpretation of gauge-invariant observables. So what's essentially the reason for this this to happen? I mean, it has to do with the redundancy, of course, that's related to the gauge symmetry. That's, I mean, it's a many-to-one map from gauge-variant observables to invariant observables. I can have many different ways in which I write one and the same invariant observables in terms of non-invariant observables. And so then that's, since I use kinematic degrees of freedom for the interpretation, you know, I get different interpretations of the same observable. Okay, now I come to the last topic. I think I will manage in 5 minutes. The quantum relativity of subsystems. Let me maybe start at a more general level that should also be true in field theory. That kind of connects with what I said here. So here we have many different ways of basically writing one and the same invariant observable in terms of non-invariant observables. But we also have sort of a converse, which is there's many different ways in which we can invariantize one and the same kinematical observable. And that's what we discussed before. We can, for some scalar field, say, we can dress it in many different ways. And we can also turn it into a relational observable in many different ways, giving us different orbits in our invariant algebra. And this is important because this means here that whatever I mean by phi, that means different things relative to different reference frames. So I get different invariant observables. I mean, this is of course already related to what I said before in the talk when I was referring to this refactorization of observables, for instance, also classically. So, but you know, more generally, you also get that in field theory. So this is then the origin of why I get a reference frame dependence of physics, such as correlations. And suppose this is now a quantum algebra. You can see why that happens, because suppose I'm looking at now the scalar field, and I'm looking at it in terms of a particular addressing, let's say, and I want to know the correlations, the gauge-invariant correlations between two dressed observables. I mean, well, the same scalar field, but you know, basically at different dressed locations. I can of course evaluate that two-point function in some physical state, and I could do the same thing with you know, two field relational observables. And since in general these orbits maybe they will not even intersect. So remember that in the field theory case, this A-phys will be an infinite dimensional algebra, and these orbits, they're going to be 4-dimensional. So there's a big chance they won't even intersect. And so, but then if I'm probing one and the same physical state with different observables, it's clear that in general, you know, the notion of correlations that I will get, that it will be in fact different. And so, so this is a qualitative argument that also holds in field theory, but one can make this actually explicit in quantum mechanical systems or quantum cosmological systems. And that's the last thing I want to talk about. So we've proven that in our recent paper. So what's the setup? So we have 3 kinematical subsystems that are subject to constraint of this form here. So, so in particular, we're ignoring interactions. I mean, in quantum theory, of course, things are often much harder to prove than in the classical case. And interactions make your life hard. So here for the starter, we have ignored interactions. And these different constrained components, they can be generators either of U1 or the translation group. They can also be mixed. And in fact, they can also have a degenerate spectrum. So the setup here encodes, in particular, quantum cosmological models where you have to worry about, you know, positive and negative frequency modes and so on. And basically, what we get here is now a frame-dependent gauge-invariant tensor factorization, or factorizations, I should say. One of the things we've proved in that paper is we're giving, in fact, necessary and sufficient conditions for the algebra generated by Dirac observables on the physical Hilbert space, subject to a constraint, for this to factorize according to the subsystems. So the subsystems are kinematically defined, I should say, right? So what I mean by A, B, C is defined in terms of the kinematical structure. And so you can factorize it relative to, let's say, subsystem C. So we choose C as a, let's say, as an example, as a reference frame. And it factorizes into across the relational observables of A relative to C and B relative to C, if and only if a certain condition on the spectrum of these objects here is satisfied. What this is in detail is maybe not so important for us here, but you can write down explicitly. So this here is basically the spectrum that's allowed by the sum of these components of the constraints subject to the constraints. And this here are what are the eigenvalues of CA that are allowed by the constraint essentially. And this here is a Minkowski sum. So if you don't know what the Minkowski sum is, doesn't really matter. It's basically you're allowed to sum any element of this one here with any element of this set here, and the set you generate thereby, that's this guy here. That's the Minkowski sum. That's maybe not so important here. Okay, so then the next thing one can ask is, well, can I also satisfy that condition here, this necessary and sufficient condition for one frame, but maybe not for another? And indeed, that is possible. So whether your system is factorizable depends in general on the choice of frame. And so we're giving some examples in that paper. So you can have the situation that, for instance, relative to C, this condition here is satisfied, and then you get such a factorization. But that maybe relative to B, this condition isn't satisfied, and then you don't get a factorization relative to B. So in that sense, whether you can factorize or not, that is already frame dependent. And then as a third thing that we look at, now suppose relative to B and C, this condition here is satisfied. So we can factorize, then we get a factorization of the total invariant algebra in terms of my first reference frame and second reference frame. But then it turns out that these factorizations are in fact necessarily frame dependent. So what I mean by that is that here the relational observable algebra of A relative to B is distinct from the relational observable algebra of A relative to C. So this thing here is not the same as that thing here. And here I literally mean distinct. So these algebras, they can be isomorphic. In general, they don't have to be isomorphic, but they can be isomorphic. But here I literally mean that they're distinct. And effectively what happens is, for instance, that while this guy here, it commutes with any of the observables inside here, it turns out that this guy here will in general not commute with elements here. So this is what I mean that they're that they're actually distinct algebras, and therefore they will give you what I write here in general, frame dependent but gauge-invariant tensor factorization. And the same then is induced on the physical Hilbert space, and in fact also in the internal frame perspectives. But I mean, maybe not go into this further. So this is essentially the last slide. So what's the upshot of this? Well, we get frame-dependent gauge-invariant entanglement. So loosely speaking, one can say what frames B and C mean when they refer to subsystem A is actually different invariant degrees of freedom. So if we have, let's say, factorizability relative to the two frames, well, that means these are different tensor factorizations. Then it's already clear that in general, the correlations and the entanglement of the subsystem A that I'm looking at in the different frame perspectives with its complements will in general differ in the two perspectives. And that's simply because the algebras, they're different. So when I evaluate these algebra elements in one and the same physical state, because I'm probing the same physical state with different algebra elements, I'm guaranteed to get in general different correlations. And in fact, and what you will also get is you will get in general different entanglement entropies for the subsystem A relative to B. This will in general not be the same as the entanglement entropy of A relative to C for the same global physical state. And I want to stress here is that what we're talking about here is really a gauge-invariant or relational notion of subsystem. And so also, when I talk about these entanglement entropies, you would define them really in a gauge-invariant way. And this is in fact quite different from what happens in field theory. A priori, when I talk about field theory of subregions like this, I mean, they're a priori not gauge-invariant notions of subsystems, right? Because I'm through the boundary here, I'm actually breaking gauge-invariant degrees of freedom that are crossing the boundary. So, but the question is, can we actually extend something that we have here in these mechanical or cosmological systems also to field theory by defining gauge-invariant notions of subsystems, for example, in terms of the edge modes. So that we use the edge modes as external reference frame to totally turn all the degrees of freedom here associated with a subregion into gauge-invariant ones along the lines of what I said earlier in the talk. And then maybe is there a way of defining subsystems in terms of commuting subalgebras when you do that for different subregions? So to define the subregions relationally relative to a frame and not just relative to some space-time region. Okay, this is really all I wanted to say. So I'm a bit over time, so maybe I'm just going to throw the conclusions here at you, and I leave them standing here, and you can read them for yourself. So thanks very much for your attention.
Thank you, Philipp. All right, we can take some questions. Yeah, Carlo?
Thank you, Philipp. I'm struggling with the light here. Can you hear me?
Yeah.
Okay, so first, thanks a lot. I mean, there was a lot of stuff in what you presented. I think it's remarkably good what you're doing. I didn't follow everything. I lost a number of technical details, but it seems to me that you're really clarifying a number of separate issues which are discussed there, which actually turn out to be aspect of the same general story. And I'm impressed by the overall clarity that you have, conceptual clarity that you have in all this. So first, congratulations. I have just one completely small remark, which is completely maybe side to what you're saying. Terminological, it might be completely nonsense. You use and also let me notice that I missed the first 10 minutes of your, because I was late. So if you have addressed that at the beginning, pardon me and just tell me. You use the terminology Heisenberg cut.
Yeah.
Which is very, it works very well. I realize how it works well in this context, and so it's very telling. It seems to be saying, but it seems to me it's a bit dangerous as terminology, because it refers to a problem which you're not addressing, in spite of the fact that this entire perspective you give on the relationality of the observables is relevant for that problem. But it's a different problem, which is a problem that happens with measurements, and when an observer measures something, and then what exactly can we say about the relation between what a given observer measures something? So a number comes out, and then another observer outside it sort of is considering the observer itself a quantum system. Now, I'm not saying that all your construction is not relevant for this discussion. In fact, it is relevant, I think, for that discussion. But you're definitely not talking about that. And when people mention Heisenberg cut, usually one think about Wigner friends, right? That's so I just wanted to your reaction about that, because it seems what you're mostly doing here is two things: a lot of technical work, which is very good, but mostly it's a conceptual clarification, which I think it's remarkable. I mean, this has to do with all this infinite confusion about the edge modes, what they mean. It has to do with, with the problem of time in which you work, has to do with the observability and general relativity. And you have a language, and this that you call neutral perspective. It's nice way of giving a unifying picture of all that and understanding exactly what happens. I mean, this is I think is very good theoretical physics. But precisely because you have this clarity, the problem of measuring quantum mechanics, which the Heisenberg cats seem to allude, you're not really addressing it now. Am I wrong, or should I?
No, you're completely right. Yeah, I have nothing to defend on that front. So,
Okay.
So no, I completely agree with you. So I'm using the word Heisenberg cut in a loose sense here. So
okay.
Likewise, when I talk about context for the interpretation of observables, it's also in some loose sense. Let's say it's by analogy with these concepts from quantum foundations, but they're not exactly the same thing. And you're of course completely right that one thing I'm not addressing at all is the measurement problem. And in particular, the Wigner-Friend scenario and so on. That's one of the things that here also in this perspective neutral approach, we haven't really addressed. Because in order to do that, you would have to indeed include measurement interactions. And that's something that actually so far we haven't really studied. So there's a lot of other problems you can still look at without doing that. And I admit that, referring to Wigner-Friend type scenarios and Heisenberg cuts, okay, is only by analogy here, but it's not exactly the same thing.
Yeah. Okay, so we're the same guy. I was not understanding you. That's perfect. And of course, names can be used in different contexts. Having said so, it's still. Let me just wait. Having said so, it's still true that all what you're doing is relevant ultimately for that quantum mechanical discussion. I think might become relevant in that.
No. So it's kind of motivated by that. Indeed, I think it's something that should be relevant for that problem. But precisely speaking, it's at this point what I mean by the Heisenberg cut isn't really yet the Heisenberg cut as usually used in quantum foundations. So I agree.
Another question?
Maybe I have one. Hi, Philipp. Thank you so much. I really enjoyed the presentation. I put a lot of things. I'm curious if you wanted to say something more about the use of edge modes as a neutral reference frame, because for my very loose understanding, you would have many different choices of reference frame. So
yes, whoops, I'm sorry, I have to understand how I go back here on this. Maybe let me do it. Sorry, maybe let me do it on my, can you see my cursor?
Yeah.
Yes. But when you use the white slides, better. Yeah, okay.
Yeah, so here, it has to do with this here. That's indeed, when I'm looking at the embedding of a subregion M that I'm interested in into larger and larger regions that are defining the environment, then I can, define more and more edge modes on the boundary of the region I'm interested in. So I get more and more independent reference frame degrees of freedom on the boundary that tell me how the subregion is coupling to whatever region outside I might be interested in. So in that sense, I can I can look at reference frame changes by this is basically what I was discussing here. If I have, so what I should emphasize is the gauge group has remained the same. Of course, the gauge group doesn't change by extending the phase space. So it's the same gauge group as before. It's just that I get more and more degrees of freedom that I can use as a reference frame, and so I can build more and more relational observables. And the more.
But my doubts. Yeah. Sorry.
Yeah, and so the more reference degrees of freedom I have, so the more reference frame changes I can consider. And and I mean, here the reference frame changes, they're really nothing but at the perspective neutral level. So when I don't go to any reduced description, they're really nothing but field redefinitions where I go and describe basically all the degrees of freedom other than the reference frame relative to that reference frame in terms of relational observables. And then I go to, whoops, what's happening here? And then I, sorry, something funny happened. And then I can go to the description now relative to different reference frame of basically the complement of the degrees of freedom of that reference frame. And that gives me a complete description of my local gauge-invariant data, but in different ways. And so, I mean, I've been very explicit here. It's, I mean, but it's at least conceptually fairly clear how it works. So here I've said a couple more things relating it to also the the sort of internal perspective changes. So, you know, at the perspective neutral level, perspective neutral is the constraint surface and the space of orbits. So the perspective neutral phase space. So here at this level, it's really just field redefinitions where you change your coordinates on your on your perspective neutral structure, but coordinates that are sort of frame specific. And then, well, and then I can also go into the internal frame perspectives by doing these removing redundancies that I have in the presence of gauge symmetries, which I get by, for instance, gauge fixing whatever I choose as my reference degree of freedom. So for example, this here could be the field space I'm looking at here. It could be the field space for the region M. So it could be the field space, you know, for basically what's in M and on the boundary, including all the edge modes that I get from the embedding into these larger regions if you want. And so I have all these different edge mode degrees of freedom in that constraint surface. And wait, what's happening here? And so I have that selection of different reference frames that I can pick different edge modes. And for instance, you know, what I call R1 and R2 here, I mean, those are reference fields. So there could be edge mode 1 and edge mode 2 if you want. And I can, for instance, gauge fix, let's say, the reduction from the perspective neutral level to the internal frame perspective of, let's say, edge mode 2 could be through a gauge fixing where, for example, I say I want to declare that my edge mode 2 is now in the orientation which corresponds to the origin. Why not? I'm free to do it because I still have gauge degrees of freedom, so I can fix them. So I'm just basically gauge fixing my gauge invariant data. I can do it, but I can also do it relative to edge mode 1, for instance. And I could say, well, I want to say that the configuration degree of freedom of the edge mode, which is group valued, it's in the origin state. So in the identity element mode, if you want. And then, but since these correspond to different degrees of freedom, this will correspond to different gauge fixings on the constraint surface. And so in these different gauge fixings, they correspond to different gauge fixed reduced phase spaces. And so they define me different, reduction maps that I can consider as the coordinate map associated with a reference frame to go to the internal perspective. And well, and the frame changes, then they work as in a mechanical example that I basically invert these, these reduction maps wherever they can be inverted, just like coordinate changes on a manifold. They will in general not be globally defined because of the Gribov problem. And then, I go from the internal perspective, I map it back to the perspective neutral structure, and then I map forward into the internal perspective. And this I can do for, at least locally, I can always do that for any of these edge modes.
Philipp, have you studied explicitly the asymptotic case? So it seems to me like the one in which you lose this distinction between internal and external perspective, isn't it?
Yeah, so I mean, in principle, if you, yeah, that's, I mean, indeed, I mean, if I include now all degrees of freedom, or for instance, if I have a closed universe or something like this, then at some point I can't extend any further. Then I just have to live with whatever I have. But still, in general, I will have a lot of degrees of freedom. In general, I will have more degrees of freedom than gauge degrees of then I have then the dimension of the gauge group. So I will in general have many choices of what I may want to pick as my reference frame. And so when I have many different choices, I can build relational observables many different ways. And then I can look again at relations between them in terms of these field redefinitions or this construction here. So I mean, this picture that I'm drawing here is not specific to edge modes. I could also use it for relational observables relative to, I don't know, dust field in space-time without a boundary. I mean, I can also do that. So the structure is qualitatively the same.
Thank you.
In fact, related to this point, I have a question. If you go a few slides back, yeah, slide 57, forward a bit.
This?
Yeah. So why do you need this extension in space-time? Why isn't it sufficient to keep a region M prime and then just consider different phis, phi1, phi2, living on the boundary of this M prime? Is this the same information that you get from?
You mean so basically that I go here and then I maybe have a different charge and I look at a different edge mode here?
Yes.
Yeah, but I mean that's not going to tell me anything a priori about how that subregion couples to a larger region, no? Because these edge modes that I then have and that I have here, I mean, they don't know anything about the dynamics outside.
Yes, but I'm saying this is what you could do if regarding Francesca's question.
I mean, I can do it. I can, of course, I can do it. Sorry, I mean, maybe I wasn't particularly clear in the talk. I mean, I was so I was only really talking about a single point on the orbit here. But of course, what I'm saying in general, you should do it for the entire boundary in order to have an edge mode field on the entire boundary. I'm sorry. So it's maybe I wasn't explicit about it. But yeah, you're right. Of course. I just didn't want to draw all of that. So,
Philipp,
mm-hmm.
I think the example Mark is have in mind, you have represented, in fact, on your picture, right? Also, it's like this psi4 and psi5 that you have in the next picture.
This one here.
Isn't it the only
I think
thing that Mark was saying? Oh.
No, I understood. Maybe correct me if I'm wrong, Mark. But were you talking about phi at different points, or were you talking about?
Well, I meant both, in fact, because you could start and end at different.
Yeah, sure. But I mean, so basically, this here does that encompass part of your question?
Yes.
Okay. Yeah, you can also do that. I mean, so basically, the examples that I'm drawing here are a small subset of the possibilities that you can do. I mean, there's many different things you can do.
Thanks.
If there are no other questions, can I continue?
Sure.
One of the things, Philipp, that I found particularly intriguing is this perspective dependence of the subalgebra structure, of the system separation structure that you come up. This is very intriguing. Do I understand correctly? This is formulate the question in the extended phase space, in the extended Hilbert space, in the perspective neutral, the neutral perspective before solving the constraint. Is in everything you're doing a clear-cut subset separation there?
No. So this here is. So when I talk about, I mean, the starting point is a constraint with, describing three kinematical subsystems. So what I mean by subsystem ABC,
yeah,
that is defined in terms of the kinematical Hilbert space. So this problem here.
So there is given in your picture the system separation. Up there, it's fixed. It's not. Nothing's going to change it.
Well, I mean, this is sort of the input, I mean, when we quantize a system, we have somehow a kinematical distinction of what we mean by ABC.
Okay.
And so that's an input. But then what I'm referring to in all this rest here is really about gauge-invariant information. So I'm actually talking about, when I talk about A-phys, that's the algebra generated by Dirac observables on the physical Hilbert space. So
yeah.
So that means these are the objects that have support on hphys and that are commuting with the C here. And so when I talk about relational observables here, so this algebra here, so this is really when I take kinematical A degrees of freedom and I write them as relational observables relative to some C degree of freedom. So I'm using C as a reference frame. So the way we do it in this paper is by using these so-called covariant POVMs to model the reference frame. So under the assumptions that we're using here, we can use these covariant POVMs to define what we mean by the configurations of the reference frame. So they encode also these non-ideal reference frames. So they're in some sense ideal that the number of the different configurations that the reference frame can take in terms of these covariant POVMs, that parameterizes exactly the orbit of the group. And so under these assumptions, you can do it, even if there's degeneracy here and so on. So that works. And then when you do it, the way we construct these relational observables is in terms of the stuff that we had defined in these Trinity papers some time ago. So, so this is basically a build up on the Trinity.
Yeah.
So, but yeah, it's very important that here, when I talk about these subsystems, they're gauge-invariant subsystems. So they're not, so this tensor factorization is a physical tensor factorization. It's a tensor factorization of the physical Hilbert space. It's not a tensor factorization of the kinematical Hilbert space. So it's a tensor factorization that's defined in terms of Dirac observables. And that's very important because when people talk about correlations, for instance, as you know, in the Page-Wouters formulation, people talk about time evolution from quantum correlations. The correlations they talk about are in fact correlations with respect to the kinematical tensor factorization, but that's a priori not physical. So this tensor factorization here is a physical one. It's a very different one than what people talk about in time from entanglement in Page-Wouters. So which is misleading. So this one here is a physical notion of entanglement. And so in that sense, we have a gauge-invariant framework, but we have nevertheless a gauge-invariant frame-dependent notion of subsystems. And so that's kind of the important thing here.
And this is what underpins the fact that entanglement can be dependent on.
Yeah, that's right. So because what I mean by a subsystem A, let's say, depends on the relations that I use to define it. And different reference frames will refer to different degrees of freedom in the total invariant algebra when they refer to A, say. So, I mean, that's the statement here, that when I use B or C as a reference frame, what I mean by A, I can express that in terms of the algebra, and the algebras are really literally distinct. So they're different sets inside the total algebra.
Clear. Thanks.
More questions?
Philip, hi.
Hey.
It's Aldo.
Hey, how are you?
Oh, good, thanks. Thanks for the nice talk. I was wondering about this last point that you were talking about with Carlo. Do you understand? Is it fair to think about this physical factorization as essential? Well, I don't want to make a long summary of my own work, but do you think it is related to the way we have been presenting gluing of subregions in gauge theories, where we have a gauge-invariant descriptions in each region, and one sees that one serves as a reference frame for the other, and in a sense, that's what I could say in its words, that's what gives rise to, in a sense, something that looks like an edge mode.
I think, I would think so. I mean, Probably, yeah. I mean, I think that relates to this last point that I'm trying to make here. Can you still see the slide, actually?
Yeah, we can.
Yeah, so I mean, the importance here that this is really a gauge-invariant or relational notion of subsystem, because that's different from, how you usually define subsystems in, let's say, gauge theories, where you just pick some subregion, cut it out, and then, well, you break gauge invariance. And here the question is whether one can do something similar to this, these physical tensor factorizations, also in field series using, edge modes as reference frames. So simply by using them as external degrees of freedom to the subregion that I'm interested in, and I use the edge modes in order to turn all the degrees of freedom inside my subregion basically into physical ones by looking at the relation of those degrees of freedom in a subregion to the reference frame through the boundary. And so I think maybe that sounds at least conceptually consistent with what you were saying in terms of the gluing, maybe.
Mm-hmm.
So I mean, one thing I'm not sure about. So I mean, the year. I mean, this is a question here. I mean, I'm not sure if that works, but I'm wondering whether it is possible to at least come up with some kind of notion of gauge-invariant definitions of subregions algebraically in terms of observable algebras in space-time, where maybe in terms of using edge modes as reference frames to define invariant observables for subregions, maybe you can find commuting algebras, at least at space-like separation, in such a way that you could talk about, subsystems in an algebraic sense. So I'm not sure if you could do it. I mean, I haven't thought very deeply about this, so I'm not sure if you could do it by looking really at adjacent regions, or let's say a region and then its entire complement in the total spatial slice. I'm not sure if that would work.
I think, there are definitely questions about if one wants to do algebraic field theory about divergences and ways of regularizing things across a sharp boundary and all these kind of things. But forgetting about these higher order details, I think I would say this is what we try to do with Enrique, and to define things intrinsically, and then they're in a sense, what we call the functional connection is essentially one of these reference frames. Is in a sense a gauge fixing, a little bit more flexible mathematically, but conceptually very similar, and can be used as I think as one of these reference frames. And in certain cases, it becomes in one. I mean, it's like having it. Defining it in a relational way with respect to the field content you already have. You don't have to introduce something external. It's kind of, we don't have many explicit examples. We have just a couple, but it's a machinery that tries to pull out these reference frames. In fact, I think that's a good way of saying it.
Sorry that I'm not mentioning here.
No, it's okay.
Here, then I guess maybe I didn't fully appreciate that in your work. No, but thanks for pointing that out. I mean, this here is just
no, it's okay. I was just
it out. So but maybe you can give me you can tell me which of the papers of you guys that is, and then might want to have a look at it.
Well,
you guys have many, so
yeah. So in the very first, we mentioned observers, and I think what we had in mind is not nearly as well spelled out as here. Is probably quite confusing. But in the first paper, we were mentioning observers, and we had in mind something similar. And regarding gauge-invariant observables, the last couple are where I think the very last one is the simplest to read, and there are references to the actual theorems. But in fact, what intrigued me was this exactly this tensor product in the physical Hilbert space. I think that's where I wanted to understand it.
Okay.
better
Yeah, no,
way.
that sounds very interesting. I'll be happy to look at it a little more at your stuff. I mean, I think you could already ask this question classically. You know, I mean, in terms of Poisson brackets, basically Poisson algebras, might be a little simpler actually.
Yeah. Well, thanks.
Yeah. There's...
Could you, hi, Philip. This is Ted.
Hi, Ted.
Could you, you mentioned that it's more complicated if you have interactions, and you're talking about one of your examples. And so
I want to see your face, Ted.
I'm lying in bed.
even more.
Yeah, you said it would be more complicated if you included interactions, so you were just considering the simpler case, but I didn't catch why it really matters. I mean, interactions are a property of the Hamiltonian, whereas what you were talking about is, you know, Hilbert space factors, and you can use eigenvalues of whatever operators you want. It doesn't have to be related to the Hamiltonian. So could you elaborate on that?
Yeah, no, I mean, so here I'm talking about basically, when I talk about interactions, I'm loosely speaking about interactions in the constraint, if you want. So there's no, we're not considering any couplings between A, B, and C. So C could be a Hamiltonian constraint, for instance. So that in that sense, there's really then no interaction between A, B, and C. But of course, you know, C could also be. Yeah, so, and I mean, it is important that there's no coupling between A, B, and C, because coupling terms, you know, they will modify what we mean by the constraint. And the constraint, of course, determines what we mean by relational observables. And the thing is, when you have interaction terms or coupling terms, things get a whole lot more complicated, because typically, if you have a generic coupling, what happens is that your reference frames, or like, you know, in the way in which we've set it up, you can use A, B, and C really as a faithful reference frame for whatever group they generate, so be it U1 or R. So in the sense that you can really use the configurations of the frame to parameterize the entire orbit. So in that sense, they're global along the orbit. But if you have coupling terms, typically what happens is that, that this messes up the reference frames. So it's like, for instance, in quantum cosmology, if you have interaction terms in your Hamiltonian constraint, what typically happens is that you get non-global clocks. So relational clocks that go forward and then backward. Like, for instance, you know, if you have a closed Friedmann universe with a massive scalar field, there's a coupling, and that actually leads even to chaos in the flow. And that's just, you know, practically you can't really solve anything there. So, let alone in the quantum theory. And so the simplification that we're doing here is really to allow us to use A, B, and C as, you know, in the sense in which I said, it's like global reference frames. Because otherwise, if you want to talk about sort of local or transient reference frames in the quantum theory, you can do it. But in the full quantum theory at a full Hilbert space level, it's really, really, really hard. So.
Mm-hmm. Well, do you regard that as a serious obstacle for this being your scheme being a foundation for understanding quantum gravity?
Well, I would say that qualitatively, these things, they should still carry over. So in particular, by what I said here, you know, these arguments that I was making here, they're really qualitative arguments, and that, you know, in principle, if I can define Drastic observables or relational observables in whatever complicated theory I have, maybe I'm not able to write them down explicitly because it's hard, but maybe they exist. If they exist, they will still define, you know, these different stratifications of my invariant observable algebra. And just by these arguments that I made here, these qualitative arguments, you know, this fact that I will get frame-dependent correlations that just should always hold, as long as I have a notion of Drastic or relational observables. So, I mean, it's a qualitative argument, and I just wanted to make that qualitative argument here, because I think it does hold generally. Well, generally, as soon as you have something like, as long as Drastic and relational observables exist, it's just hard to prove. And to make these things more explicit, you know, I went then to a simpler scenario where you can actually prove stuff.
Mm-hmm. Thank you.
can I ask one question?
Sure.
Hi.
Sure.
Hi, Philipp.
Hey.
Can you indicate for me which further simplification arise in the quantum case when you assume when you are in approximation in which the reference frame becomes semi-classical?
I mean, I'm not sure if there's really much more simplification happening because, I mean, here in these, are you referring to the setup here or?
Well, here or in the covariance?
So, I mean, this here also refers to covariance when I have these different refactorizations. Yeah. But the thing is that, you know, in these arguments, what is important is, I mean, for proving it is that these reference frames are global in the sense, so along the orbits, whether they have classical properties or not is actually irrelevant at that point. So, but there will be simplifications happening if you have, if you're looking at, for instance, constraints with coupling terms, and then maybe you want to do a semi-classical treatment, for instance, along the effective treatments that you well know of. Then, yeah, I mean, then I think you can also do many of these things more generally, also for yeah, at a semi-classical order. So, but this would of course mean that all degrees of freedom are in some sense semi-classical, or that your physical state you're looking at is semi-classical. So in that sense, yeah, you can of course you get a lot of simplifications because you know, if I have something like a non-global reference frame, like a clock with turning points, this is a serious problem when I have like really highly fluctuating quantum states, where then I can have you know, superpositions of forward and backwards moving modes of the relational clock. But if I'm in semi-classical or very peak states, then, well, you know, at least approximately, you can kind of ignore those. And so in that sense, you can, you know, treat things a little nicer. But at least for the yeah, but otherwise, you know, for this argument, as long as you have globally valid reference frames, then it doesn't matter whether it's semi-classical or not. I mean, it works either way.
Okay, thanks.
Yep.
A final question, maybe? If not, we can thank Philipp again for the great talk. Thanks.
Yeah, thanks guys for the attention.
Yeah, thank you for joining us, and we'll see you in 2 weeks. Hopefully.
Right.
Thank you.